concentration factor for pure tension and pure torsion. For this test specimen, I used an axisymmetric model in Abacus, and sum the nodal forces and moments along a hypothetical cut, that's the purple line at the weld toe, to produce consistent results for a varying number of through thickness elements. Those stress concentration factors are then applied to plot the multi-axial load paths in a structural normal stress and structural shear stress planes. The shear plane has a scaling factor beta, which is a relationship between the pure tension and pure torsion SN curves, similar to the K value in the interaction equations. Since tension and torsion SN curves have different slopes, the K and beta value both vary with N, so it's common to just use a constant average value. For the simple sinusoidal and constant amplitude, constant frequency loading in this experimental data, we have elliptical load paths, which are shown in figure 4, the length of which is the effective stress. The value GNP is a general non-proportionality constant that evaluates the effective non-proportionality or out of phase angle, which we see increases with phase angle in figure 5, discrediting the constant value that's suggested by our current industry standards. Finally, the effects of thickness and loading ratio get factored out in the load path base parameter equation, which is the bolded equation at the bottom center of my poster. This allows us to plot the data on the ASME master SN curve, which is a singular SN curve that correlates thousands of data points of varying joint geometries and loadings. Key findings include a path length effective stress SN curve, that's figure 6, yields a mean curve that passes through the mean of each individual data set, the pure tension, pure torsion, proportional, and all non-proportional angles, which is significantly improved data correlation than the IIW, DNV, and Eurocode interaction equations, and quantitatively less scatter. So to point that out on the IIW curve, that's in figure 2, on the top left, note particularly the locations of the pure tension and pure torsion. Those are the black filled in and empty circle data points, and the proportional data set in red in relation to the mean dotted curve. In the path length based SN curve to the right, everything is collapsed, so the mean dotted curve again passes through each individual mean. Additionally, the analyzed data is consistent with the ASME master SN curve scatter bands that's shown in figure 8. This is significant as enhanced data correlation and transferability of data will result in less need for very specific joint and load data, which is incredibly time and cost consuming, and ultimately better fatigue design. I will say this data in this study was limited to constant amplitude and frequencies, so kind of the simplest cases. So next steps include analyzing more complex loadings to really demonstrate the additional benefits of this method. Thank you.
Awesome. Very good presentation. I'm glad that there are people like looking into the mechanical performance as well for welded joints, not only the process side. So I'm going to open now the floor for questions. So Jack?
Yeah, thank you for the presentation. It was just to hear a little more about what you said in the end about looking into more complex loading. What exactly are you thinking of looking into there? What kind of more complex loading?
Yeah, so one of the main benefits of this method over the conventional methods is that it can deal with more complex cycle counting. So really, I'd like to look at non-constant amplitude, non-constant frequency, because that's really what we see in ships, right, with our crazy sea states. So yeah, the next round will hopefully have some of that data in order to show how this method can account for cycle counting, really.
Okay, thank you.
Mm-hmm.
So next, Thomas.
Thanks for a nice presentation. It's going in terms of mechanics far beyond my knowledge in fatigue. That's why I have rather a process-related question. Did you use arc welded samples for the experiments, I assume?
Yes. And yes, this was not my data. This was from Nana Winter. She's from Denmark.
It would be interesting to know if this approach is only valid for arc welding, or is it possible to use it also for different welding processes, also for circular welds? I mean, if you have something which is fraction welded, maybe, or something like that.
Right. So the ASME master SN curve does have correlated data points for all sorts of welding processes. This is the first I've used it for particularly the path length method. So yeah, I don't believe it's been really tested for multi-axial fatigue, but the ASME curve does have data points from other welding methods.
Oh, thanks. Thanks. Keep going. Nice job.
Thank you.
Gazal?
Yeah, thank you, Tara. It was a really good presentation. I had a chance to hear your presentation also in Genova. Yeah, I want to ask you about the fatigue or welded failures. When we have kind of failures like a porosity or debonding, should it be considered in your model a bit later, or it is not a possibility to include such a failures?
So we factor those failures really in the data from the SN curve as opposed to in the model themselves, just because our welds tend to get inspected. So yeah, we factor those kind of failures into the SN curve data as opposed to the actual models.
Because at the beginning you mentioned there's a recommendation from Professor Hobacher from IW, and he has a part that is considering the fatigue, the weld failure, and like porosities and the percentage of the porosity and the behavior on the fatigue behavior. So I think in the future it would be great if the model could be developed to also simulate or consider also failures, weld failures.
Okay, great. Yeah, I'll look into that. Thank you.
Great. We have 1 minute for one quick question you guys have. Awesome. So we can move on. Then next presentation is going to be Mia. She's going to present assessing mechanical property sensitivity to sampling location in wire arc additive manufacturing components.
Hi, everyone. I'll just share my screen. Can you see my screen?
Yes.
Perfect. Okay. My name is Mia Abdullah. I'm a master's student at the University of Alberta up in Canada, so where it's pretty cold right now. I'm going to be talking about some of the stuff that I've been doing, assessing mechanical property sensitivity to sampling location in wire arc additive manufacturing components. Just for a kind of a brief overview, additive manufacturing is usually treated as a bulk homogeneous structure when we're in testing. But specifically wire arc additive manufacturing, with the constant thermal cycles going through with each bead being deposited, it could create kind of different zones. And we want to highlight that in this project to allow us to test better or just to give us some more information. A little bit of background into the project. In the introduction, so ASME Section 9, Article 6, QW 600 was recently introduced in the ASME code sections for pressure service additively manufactured parts to support the qualification of AM parts for pressure service in our Alberta or North American industries. Up in Alberta, we have a very, very strong oil and gas industry, which has a lot of pressure parts. You can see kind of in upcoming works, that's how the project was originally started. It was based off of pressure parts like flanges. So we want to see how parts in service, additively manufactured parts in service, can be tested properly. So going back to the introduction, QW 600 was introduced, and you can see that first picture, figure QW 461, is how you test multi-bead additively manufactured qualified parts. You can see both the Sharpie V-notch testing and the tensile bars aren't in specific locations, and they're quite vague. Moving into ASME section 8 for a bit of maybe further clarification. For normal welding, you have Sharpie V-notch coming out of either the has or in the weld material. Obviously, in additive manufacturing, everything is weld material, but it does have those thermal cycles, so we don't know entirely where we should be taking out of it. To look at this, we used the Lincoln Electric Sculpin R&D WAM machine, and we built up a wall 9 beads across and 150 layers up, so it was about 9 inches high. We had 9 beads going across, and every layer we switched the travel direction by 180 degrees. We wanted to keep the travel speed constant, so we wanted to prevent like a dragon back profile or a sloped wall, if you would. So we switched travel directions. After the wall got sliced into about 6 sections, 5 of those went for tensile and bend testing, or is in the process of being cut for tensile and bend testing, and the other section went in for Sharpie V-notch testing. So we machined all of the 6 components, and then we macro etched it with using 10% nitol. And you can see, I'm not sure if you can see, but maybe I'll zoom in. We have a bead profile that you can see, and that way we can locate each sample, whether it be tensile or Sharpie, in a specific region with specific thermal histories. So out of the Sharpie V-notch, you can see the green is within a layer, but along many beads. The orange is between layers. The red is going between beads, and the blue is going between layers. So we're getting either a homogeneous crack profile or an inhomogeneous crack profile. The tensile has 2 orientations, one coming out specifically for qualification for QW600, and the other orientation on the side is for an additional orientation to give us a little bit more information, positioning either the tensile within a bead entirely or within the tempered regions between the overlap of 2 beads. For preliminary results, like I said before, this is going in for testing in the next couple weeks, but a couple things that I wanted to show right now is we took a section of our wall and we did a hardness map of it. So what you can see there is about 20,000 indents of the wall's profile, and you can see that there's clearly 2 zones, one a lot harder and one a lot softer. So one is in between 2 sets of bead, or that overlapped section, and one is directly in the bead. Same thing for the layer, either the tempered region of the bead going on top of the previously deposited layer, or that harder zone where it wasn't tempered. So it shows 2 distinct regions. So we want to show those results coming up later on. For the tensile and the Sharpie, you can see 2 of the major regions. You have either in the tempered zone or in the non-tempered zone. So picture A shows the tensile gauge entirely in 1 bead, and then tensile gauge number 2, we wanted a reheated zone between 2 beads going down the center of that gauge. So we're hoping to see 2 different fracture analysis samples coming out of that. Here is that top part of the wall. These are the 9 beads depositing, and then the tempered zones in between. So we're going to take samples out of each location. For upcoming
you have
work,
30 seconds, Mia, to wrap up.
Gotcha. For upcoming work, we want to conduct the mechanical testings for these walls, and then also evaluate the implications for sampling location sensitivity for real-world geometry. So you can see those flanges that we built out. We want to see exactly where we want to pull those tensile or Sharpies out. I want to thank Lincoln Electric and Apollo Laser Cladding for all the help that they've given me over the past year and a bit. And that's it.
Very good presentation. Congratulations, very good work. So now we're going to open to questions.
For sure.
Any questions? Don't be shy, guys. Oh, I'm going to start then. I know that I watched your presentation at FabTech. It was pretty good. I don't know if I asked you this question, but I'm going to point out. So one of the main issues in the additive is the residual stresses, right? Yeah. And I don't know if the standard takes this factor into account, but are you guys looking into adding such a parameter into consideration for 3D printed parts?
Yeah, so this specific project is done with carbon steel, so ER70. We haven't had much residual stress done specifically with the flanges, but we're following up with another project coming up, and it's entirely based on qualification gaps with residual stress for these additively manufactured parts, looking at a martensitic steel. So yeah, that should be coming in the next couple months.
Mm-hmm. Rocky, I saw you kind of raised your hand for a second.
But you asked my question, so
Okay.
Okay.
don't worry. I was gonna ask the same thing. Great work,
We definitely
though.
know that residual stress is a big point for additive manufacturing, and for people to
Yeah.
get clarity and trust on these parts, an answer definitely has to be spoken about. So it's definitely something that we're gonna look into.
I think this is a really great lack, though, that exists in the standards right now. So it's really impactful work. So great job.
Thank you so much.
But maybe in this case, it is a bit hard to work on the standardization of the components when we have such a kind of multi-layers and each layer with different deposition parameters. It is in Germany, maybe for most of the industries, it is a bit hard to use these components for Airbus or so on.
For sure. I completely
But
agree.
are you considering such a kind of active cooling or passive cooling processes to not get rid of, but to reduce the residual stresses?
As of right now, we're not active cooling. We have an interlayer temperature between each bead that we're setting. So right now with the carbon steel based on API guideline in Alberta, we have it set at 315 degrees, and that will change depending on what material we're using. Active cooling we haven't started, but I know other people have, and they've had tremendous results. So it's definitely something we should think about.
Great
Great.
job, Mia.
Thank you.
Any other question? If there is no question, just a quick one. Are you considering any modeling in your work, like for later on mapping the thermal cycle through the whole part, for example?
I didn't show it here, but we have a thermal simulation of the parts that we printed, just to get an idea of residual stresses and just thermal gradients as we're progressing in the print. I didn't show it here, but maybe I'll show it in my next presentation where that'll be. I don't know.
At IW, maybe.
Perfect.
Yeah, maybe
Okay.
in Austria.
Yeah, maybe
Yeah.
Austria. Maybe I will show it there. Thank
You
Hello.
should tell Patricio to sponsor your travel there. So tell him to find the fund.
I will. I'll give him the message. I'll give him the message.
Great.
I might have a question as well.
Yes. Who is talking?
If you already have a Lorenz Willenberg from Germany,
Got it.
colleague of Tamas. If you are already having a thermal simulation of your part, are you thinking about coupling it to a mechanical or even a simulation of the phase development regarding the Martin? You talked about doing the same work with martensitic steel.
Yes, so we are going to do the same thermal system for the martensitic steel. We haven't started that, and maybe it's going to be future work for Austria to be shown. We'll see. Yeah.
Okay.
Great. So now it's time to move to our very last presentation. So Xiaoyi Zhao is going to present evaluating the mechanical contribution of silicon-induced precipitates in copper silicon 3D-based laser-brazed metal.
Yeah, so thank you very much. Can you see my screen now?
Yes, very clear.
Yeah, thank you. So thank you very much for having me to give this presentation.
I'm sorry interrupting you, Xiao. Can you please put in the presentation mode?
Okay. Okay, good.
Perfect, thank you.
Yeah, let me change my laser pointer. Yep. So thank you very much for this opportunity to share my research with you. So I'm Xiaoye, and I'm a PhD candidate from University of Waterloo, and my topic today is evaluating the mechanical contribution of silicon-induced precipitation in copper silicon 3 based laser brazed metal. So first, introduction of the laser brazing. So as you may know that advanced hydrogen steel has been used for automotive industry, and zinc coating is used to protect the steel from corrosion. But we have some other challenges for the fusion welding of zinc coated steel because the low and melting and evaporating temperature of zinc can cause some surface imperfections for the fusion welds, such as let's say the surface spatters, pores, and also zinc burn off and others. And that's why we have this research for the non-fusion welding process such as brazing. And laser brazing is one technology used in automotive industry for the joining of the roof and the body side panel, and also for the hatchback parts where the high surface quality is required. And my objective for this work is to investigate the strengthening mechanism of the silicon-induced precipitates when use copper silicon 3 wire. And on the left, I have a schematic for the experimental setup. So I have like two L-shaped steel, and the base metal is deposited in the middle of the steel. I use a copper silicon 3 wire, which contains about 3% of silicon. I also use a copper wire, which has light silicon for compression. So the general results, let me zoom in. Yep. So first, we see this primary precipitates within the brazed metal. The dimension is about 1 micrometer. But very differently, we also see some secondary precipitates in the copper silicon 3 brazed metal, as you may see in as the white dots in the black precipitates. And then I take the OJ analysis. It shows, okay, we have the copper and the silicon in the primary precipitates in copper silicon 3 braze. But for the other one in the copper braze, we see like a trace amount of copper, almost no silicon inside that one. So that gives us an idea, like, okay, the secondary precipitate is kind of copper silicon intermetallics. And then move to the tensile test. Okay, so for the copper silicon 3 braze, it shows a higher tensile strength compared to copper, but it shows significantly higher tensile strength compared to copper braze metal. So what's the reason for the improvement of this mechanical performance? And then I check the SEM for this fracture sample, and I see the crack initiate inside the primary precipitates for the copper silicon 3 braze, but there are a lot of crack at the interface of the primary precipitate and matrix for the copper braze metal. And then I take one of these primary precipitates in copper silicon 3 for TM analysis. So here's one particle I take, and then I take the interface for high resolution TM analysis, and I found that, let me zoom in. I found that this matrix is copper, so which is very obvious, and the precipitates is iron phase. And very surprisingly, they show coherent relationship. So that's very surprising because we know that copper and iron, they are immiscible system. Usually they just have this liquid metal separation and other segregation, but now we have coherent relationship. And also I see a lot of kinks at the interface. So the kinks is formed because the stress accumulated at the interface. And I also am able to index all these diffraction spots from this image, so which is the copper, iron, and also kinks from copper and iron. And so the question is still, so how we have the coherent relationship now? So I did one thermocalc, which help us understand this. So we have 3% silicon and 0.5% of the silicon. And when we have lower silicon, the solidification process is very direct and clear. So we have the iron iron formed first and then copper. So they are separate processes. But when we have 3% silicon, so the solidification is kind of complicated, but most importantly, I want to show you for the pink curve here, we have this co-formation of the iron precipitates and also the copper matrix. And I think this is the reason for this coherent relationship we show here. It's almost done, right? Yeah, okay. And then, and also for your information, I take this secondary precipitate in this green. For TM analysis, it is copper 5 silicon, and it also show coherent relationship with the matrix. But we see severe distortion at the interface. And then I believe this is one of the main reason for the crack initiate inside the primary precipitate we see here. So to conclude this work, so I found like a primary precipitate and a secondary precipitate in copper silicon 3 bridge, but only one primary precipitate in copper, and the silicon contributed co-formation of the iron and copper, which contribute to this coherent relationship and also contribute to the improvement of the strength and the stream. And finally, I also found like some stress accumulate at the interface of the secondary between the secondary and primary precipitates, which is the main reason for the crack initiate inside the particle for copper silicon 3. Yeah, thanks for your attention. Yeah, please let me know when you have any kind of question.
Awesome. Very good work. Very good presentation, shall we? So now we're going to open for questions. Any questions? Come on, guys, let's wrap up this event pretty well. So I have a question though.
Yeah.
So from an application point of view, like, how do you think these silicon-induced precipitates they will affect the overall performance or reliability of that laser-brazed joint? For example, we've been looking into corrosion.
Yeah. For corrosion, so I'm not even you mean the corrosion for the base metal, so I'm not sure that's kind of my future work I'm trying to do, because you see we have this stress accumulation, and I believe this is not good for the corrosion resistance. But we don't know. But and for the copper one, it's just like a zero, even not coherent. I'm not sure which one is better or not. That's part of my future work. And about the silicon on the strings. So according to the current work, so silicon can improve the tensile strength and also the tensile stream. But the question is, so what kind of silicon content range? I mean, how about we have 10% now? How about we only have 1%? So that's another topic I want to research, like what kind of range is best for the improvement. Yeah.
Thank you. Ghazal?
I have a very short question about the preparation of the sample for TEM characterization. Maybe it's a bit in details of the experiments. Yeah. Can you give a very short overview how you prepare the samples for TEM?
Oh,
because
for the yeah. So I use a FIB. So in general, the TEM sample is prepared and use a FIB to take use a FIB to take a thin film from this place. Yeah, use a FIB.
Okay.
Yeah, and I also want to clarify, like for the tensile sample, this tensile sample, the sample is directed from the only the base metal along the welding direction. So none of the steel is included in this tensile test. So it's just for the base metal.
Okay.
Yeah.
Perfect.
Thank
you so much. And Martin, are you also planning to consider this in situ tensile test? Also, all these tensile tests, they are not in situ, but maybe for these joints, it would be crazy to have these results.
Yeah, thank you very much for the suggestion. Yeah, that's kind of ongoing work now. I'm preparing the sample for in situ the tensile, and the question like a little challenge for me now, because the equipment we have, I mean, and our sample, like, I mean, it's just for the fixture process. It's kind of challenging now. I'm trying to figure it out. And also another challenge, I'm not sure if I can capture like this small size, I mean, the deformation along this small size precipitates. So yeah, I will try. Thank you very much.
It would be really amazing to have this small sample, miniature samples from these areas. And I know how challenging it is to fix the samples for the tensile test to be really, really accurate. Thank you so much for your work.
Thanks so much for your suggestion.
Awesome. We still have a minute left. Somebody want to give a comment or question, or shall we, before we wrap up? Okay, so with that, we close the day one. We are a little bit over time. I hope this is not gonna fire me from my chair job here. This is gonna be on Gazal and the other people. So
very
now I'm gonna
well
press
done
the ball.
job. Very well done job, Kawai. Thank you so much for all the presenters, all the attendees. It was a great thing to see that they are amazing, high quality poster presentation for today. I'm so surprised about that, and it makes our job a bit hard to find the winner for the best papers award. To be fair, all the presentations today, they were amazing. They were really good. So I want to encourage you all, please attend and join us in Austria. I would be really grateful to have you all there. And believe me, it is a really good event. And we can talk about all these things in person. When you have a chance to visit us or join us in Austria, it would be great. So thank you so much. We will see each other tomorrow at 11 o'clock. Although a bit opening, it is 10:55, and it would be great to have you all tomorrow.
Thank you everyone. Bye.
Thank you,
Have a nice
everybody.
day.
Thank you very much.
Thank you.
Goodbye,
Thank you,
everyone.
Kawai.
Congratulations.
Day.
Thanks, everyone.
Until tomorrow. Bye bye.
Bye bye.
Hasta la mañana.
Bye.